Particle physics. The fundamental idea that all physics in its smallest form can be described as particles interacting.
Let's start by breaking down something familiar, the helium atom. The helium atom is composed of a nucleus with 2 neutrons and 2 protons, and the nucleus has 2 orbiting electrons. However, protons and neutrons are not fundamental particles themselves. If you look closer, they're actually made of smaller particles called quarks.
The proton has 2 up quarks and 1 down quark. The up quark has a charge of plus 2/3, while the down quark has a charge of negative 1/3. This gives the proton the familiar +1 charge. On the other hand, the neutron has 2 down quarks and 1 up quark, which gives it a 0 charge. These quarks are held together by gluons, which we'll explain in more detail later. These quarks are fundamental particles, which means they can't be broken down into smaller parts. They're catalogued in something called the Standard Model. There are 6 quarks in total. The up, charm, and top quarks all have a plus 2/3 charge, while the down, strange, and bottom all have a negative 1/3 charge. The up and down quarks are called the first generation, the strange and charm are called the second generation, and the top and bottom are called the third generation. The higher the generation, the heavier the particles. The electron is a fundamental particle. It's in a separate category of particles called leptons. There are 6 leptons in total, with the electron, muon, and tau all having a negative 1 charge, and each of these has a corresponding neutrino, which has no charge at all. Now, to understand why we have leptons and quarks, we must understand the forces in particle physics. There are truly only 4 fundamental forces in physics. These are the strong force, electromagnetism, the weak force, and gravity. These forces are also expressed by particles called bosons. We mentioned in our discussion of the helium nucleus the gluons which hold the quarks into protons and neutrons. The gluon is the boson that corresponds to the strong nuclear force. Note that the strong force not only holds the quarks into protons and neutrons, but also the protons and neutrons into the nuclei. As the name suggests, the strong force is the strongest of all the forces, at least at short distances. This is why protons can be held so close together in the nucleus even though their same charges should really repel. The strong force is just much stronger at these distances than the electric repulsion. Furthermore, the difference between quarks and leptons lies here. While quarks interact with all the forces, leptons do not interact with the strong force, and gluons have no effect on leptons. In classical electromagnetism, we look at electric and magnetic forces as related and describe light as oscillations in these fields. It's also related to charges and explain why positive nuclei and negative electrons would attract and hence bind atoms together. However, the more modern particle physics theories describe this oscillation as a photon, an excitation of the electromagnetic field. This photon is the boson of the electromagnetic force, which is the force that holds the electron and the nucleus together. Next, we have the weak interaction, which plays its role in radioactive decay. Let's have a look at beta decay, where a neutron turns into a proton and an electron. If we look at it at a more fundamental level, it's a down quark decaying into an up quark with a W- boson. The W- is one of the bosons corresponding to the weak force. This boson then shortly decays into an electron and an anti-electron neutrino. The anti-electron neutrino is the antimatter twin of the electron neutrino. We'll get into antimatter in more detail later. When it comes to particle physics, gravity is really the elephant in the room. It's described by Einstein's theory of general relativity, a theory not easily compatible with the rest of quantum and particle physics. Although people have proposed the graviton, no such particle has been experimentally detected. Okay, that's a lot to take in, so let's have a quick recap. On one side we have bosons. Force-carrying particles, with each force having its own set of bosons, all having been detected except for gravity. On the other side, we have fermions, which can be further divided into leptons and quarks. Leptons are fermions that do not interact with the strong force. Some examples are the electron and the positron, where the positron is the antimatter twin of the electron. Now, antimatter is basically like a negative version of matter. It has all the negative values of its matter twin, but the same mass as its twin. For example, the positron, which has a +1 charge but weighs the same as an electron. Whenever a matter and an antimatter pair meet, they annihilate and give pure energy. Now, these ideas should form a very basic platform to understand some of the principles in particle physics. We'll next be looking at special relativity. If you're keen for more of the same, we have a shorter video with some of the more advanced topics in the Standard Model and particle physics in general. Otherwise, please have a look at our video on special relativity.